Hello and welcome. In this video we are going to look at the relationship between current and potential difference, and we're also going to look at another value called the resistance, and we're going to see how these three are all connected with each other. But for the first part of the video we want to look at the relationship between potential difference and the current that flows, and we can do that experimentally by looking at a circuit that looks a little bit like this. We've got a battery here which is just two or more cells together. We've got an ammeter which measures the current. We've got a voltmeter which measures the potential difference or voltage, which is the same thing, and we've got a fixed resistor, and this fixed resistor is a resistor that has a fixed value, a value that doesn't change. It's important to also mention that in this we have to assume that the temperature stays the same or the temperature is constant. Okay, now if we were to put a range of values in for the voltage, or if we were to measure a range of values of voltage or potential difference across this resistor, we could also measure the current that flows for that potential difference, and we could plot it on a graph. The numbers aren't so important here, the more important thing is what the graph looks like. So if we had a certain value of potential difference, we could plot a certain value of current, and what we would find is as we increase potential difference, the current also increases in a proportional way. And what we can do is we can join those points up, and if we've measured carefully and carried out the experiment carefully, we'll find that they all lie on a straight line. What this graph is showing us is that for a fixed resistor, the potential difference has an effect on the current, and the exact relationship is this: current is directly proportional to the potential difference across a fixed resistor when the temperature is constant. So what that really means is if you double the potential difference, you're going to double the current, and that's what we mean by directly proportional. Now this is not the whole story, because there's another part of the graph which goes into the negative values. So where we've got positive potential difference and positive current here, if we go backwards on this line here, we go into the minus values for voltage, so -2, -4, -6 and so on, and for the current into minus values as well as we go down. Now the way that could happen in the circuit is if we flip around our battery, what would happen is you would start getting minus readings or negative numbers recorded on your voltmeter and on your ammeter, but the graph would still have the same shape or the same straight line relationship. So it would actually look like that. So what we're saying is we have a straight line relationship even for the negative values here, and you should be able to recognize this graph as the graph that shows potential difference versus current for a fixed resistor. Okay, so that's the relationship between those two things. Now what we're going to look at next is a formula that you are required to use, and the formula looks like this. It says V equals I times R, sometimes it's written as V equals IR, and you'll be given this in the exam. And if you want to see what other formulas you're going to be given in the exam, have a look at the website my-gcsescience.com. On the additional science page there is the formula sheet that you can just download and have a look at, so you know. Anyway, you'll be given this in the exam, and you'll also be given the meaning of these different symbols. So V stands for potential difference, which can also be stated as voltage. I stands for the current, and R stands for resistance. All these are given to you in the exam on the formula sheet. What's not given to you though is the unit. So for potential difference it's volts, with a letter V. We've got current, which is amperes or amps with capital A. We've got resistance, which is in ohms, and it's given this symbol here, which is I think omega in the Greek alphabet, but that's the symbol that's given, and that's what it means, and it means ohms. Okay, so you won't be given these in red, so you must know and remember those. The other thing of course is being able to use the formula, and that's quite straightforward. In this example I've given here, I've got a current of 2 amps and a resistance of 20 ohms, so the voltage or potential difference would be 0.2 times 20, and that will give us a value of 4, and it's voltage or potential difference we're working out, so that's 4 volts. The other thing however is that you are also going to be asked to be able to work out any one of these values given the other two, and that means being able to rearrange the formula. Now you might be quite good at maths and quite happily able to do that, But if you want a slightly shorter method, you can use something like this called the formula triangle, which I'm sure you've seen and come across before, and it's just a way of working out one value once you know the other two. And we're going to use this now for a couple of examples. So there's our formula triangle ready for us to use, and I've got a question here. I don't know what R is, I don't know what the resistance is, but I do know the current and I do know the potential difference across that resistor. Okay, so how would we work that out? Well, we'd go to our formula. We want to work out resistance, so we can just cover that up, and we have resistance is voltage or potential difference over current, and that over just means divided by. So for the first question here, we would have resistance equals potential difference divided by the current, and that's just very simply 20 divided by 0.5. The answer would be 40, and it's resistance we're looking at, so don't forget the units. It's 40 ohms. Okay, so that's a fairly straightforward example. The second example, which I think I might have written all over, yes, never mind. Second example is actually a bit more straightforward. It's just like the one we've done. We're working out voltage, and if we were to cover up the voltage or potential difference, it's I times R, so very simply it's 0.5 times 50, which will be 25, and remember it's potential difference, so it's in volts. And the third one here, slightly less straightforward. We are required to work out the current in this what we call a parallel circuit, and the parallel circuit is one that has branches, and because it has branches, if we're working out resistance or current in this case, we have to work with that particular branch. So what we have to do is just focus on that area there for working out the current in A1. So what we do is we say, right, we want the current, so for the current we would use our formula triangle, cover up current there, and we know therefore that current is voltage divided by resistance. So for 3 part A, working out A1 equals voltage divided by resistance equals 18 divided by 10, and therefore the answer is 1.8, and don't forget the units, amps. Okay, now if we're going to work out the same for the second one down here, we have to focus on that part of the circuit. The resistance in this case is different. It's now 20 ohms. So the way we would do that is for A2, it's voltage over resistance, so it's 18 over 20 this time, and that will give us a value of 0.9 amps. So that's how you use the formula and the formula triangle. You should be able to either rearrange the formula or just use it in the way that I have done there. You should also, from the previous part of the video, be able to describe the relationship between the voltage and the current across a fixed resistor. That's me done for the moment. Thanks for watching, and I'll see you again soon.